Good morning. What I'm going to introduce today is the determination of the permeability function for high volume change materials. The presentation covers the introduction, the theory, the revised theory, and the application of the revised theory, and then at the last, the conclusions. So the coefficient of permeability is very important. It is required in the numerical modeling. The correctness of the coefficient of permeability is it guarantees the good results in numerical modeling. So the error in the coefficient of permeability would cause incorrect results in the numerical modeling. There are two factors that control the coefficient of permeability, and they are the degree of saturation and the void ratio. So it is very reasonable to estimate the coefficient of permeability by considering both degree of saturation and the void ratio. But for materials that do not undergo volume change, like sands and silts, only degree of saturation that need to be considered. And upon such assumption, there are lots of estimation techniques that have been proposed, like Van-Newton burden equation, Van-Newton-Mellem equation, and Ferenczi-Wang permeability function are three well-known permeability functions in the literature. But for high-volume change materials like Regina clay or oil sands tailings, both degree of saturation and the void ratio should be considered. And then this study proposed a revised estimation for the estimation of permeability for such kind of materials. So for the theory, covers three parts. And the first part of the shrinkage curve, it builds the relationship between the void ratio and the grammage water content. And the soil water characteristic curve is the relationship between the water content and the soil section. And the coefficient of permeability function is essentially constructed based on these two curves, the shrinkage curve and the soil water characteristic curve. For the shrinkage curve, Murray-Fernland proposed a hyperbolic equation to best fit measure data from shrinkage tests. It is a mathematical equation, empirical mathematical equation that describes the relationship between void ratio and grammatical water content empirically. This equation has three fitting parameters. And then it works well to best fit this shrinkage test. For soil water characteristic curve, there are three designations of water content. The first one is grammage water content. It refers the mass of water to the mass of solids, and the instantaneous volumetric water content, it references the volume of water to the instantaneous total volume. And then the degree of saturation, it references the volume of water to the volume of the total volume. For the no volume change soil, it doesn't matter which destination or grammage or which destination water content to use, because a soil water characteristic plots based on these destinations, they provide essentially the same information to engineer. But for the soils that change volumes, they're using different designations of water content in the soil water characteristic curve. They essentially show different shapes, different characteristic curve, different characters. So it should be remembered that it is the degree of saturation soil water characteristic curve should be used to estimate the coefficient of permeability, and also the instantaneous volumetric water content (SWCC) is the curve that should be used for the estimation of water storage function. So the coefficient of permeability is a product of the relative coefficient and the saturated coefficient. Here, the saturated, I put P in the sub-index in the saturated permeability because it doesn't mean the soil is saturated at the soil section, but it is the saturated coefficient of permeability corresponds to a vol ratio at this soil section. And originally, the Feixia-Zhang permeability function takes such kind of form. It uses volumetric water content (SWCC) to estimate the permeability. It produces very good results for no volume changing materials, but for high volume changing materials, using different soil water characteristic curves, it produces different results. And it is the second equation here, using the degree of saturation soil water characteristic curve. It produces correct results for the estimation of coefficient of permeability. To describe the relationship between the saturated permeability and the vol ratio, there are two equations we can use. One is proposed by Taylor in 1948, and the other is proposed by Somogi. And so here is a whole picture for the estimating procedure for estimating the coefficient of permeability for high volume changing material. The first step is to obtain the 15 parameters for the grammatical water content (SWCC) using Feixia equation, and the second step is to obtain the 15 parameters for the shrinkage curve, and then we calculate the vol ratio versus the section. Use these based on these two equations from the grammatical water content (SWCC) and the shrinkage curve. And the degree of saturation (SWCC) could be calculated using this basic volume mass equation. And then the instantaneous volumetric water content (SWCC) can also be calculated based on grammatical water content (SWCC) and the vol ratio and the shrinkage curve. And the relative coefficient of permeability could be obtained from the soil water characteristic curve, and using this degree of saturation versus soil section relationship. And then after we having this, now we have this relative coefficient of permeability, and then the next step is to obtain the saturated coefficient of permeability versus soil section. And this is the equation that we could use. And then after we have the saturated coefficient of permeability and the relative coefficient of permeability, by multiplying them together, then we have this coefficient of permeability function for high volume changing materials, and we are considering both degree of saturation and the vol ratio. And for the water storage function, it is obtained from the instantaneous volumetric water content. Here is an application of this revised theory on total tested thickened tailings. Total tested thickened tailing is one typical soil that undergoes volume change and soil section change in the drying process. This tailing, I used two samples, and when it's box 11, it has a sand-fine ratio equal to 0.8. It has a liquid limit of 35%, a plastic limit of 15%, and then box 2, its sand-fine ratio is 0.0, it has a liquid limit of 55% and a plastic limit of 22%. So for the first step is, so we will have the data from measure data from a shrinkage test, and we use Murray-Freiland's shrinkage equation to best fit these test data to construct a mathematical relationship between the water ratio and the grammage water content. And then we will have tests from the solid characteristic curve, and what we get, the data we get is the grammage water content versus soil suction. And by using Freiland's equation to best fit these test data, we have this mathematical relationship between the grammage water content and the soil suction, all of those are the best fitting is obtained by regression analysis. And here is the relationship between the saturated permeability and the water ratio, and also use regression analysis to best fit these data to obtain an equation, to obtain the fitting parameters for this equation. And then we will get the degree of saturation based on basic volume mass relationships. And then for these are two curves for two samples. The red one is for the box 2, which has a sample ratio of 0.1, and the blue one is for the box 11, which has sample ratio of 0.8. They show very and from these two curves, we can obtain our air entry value in an empirical way, and the air entry value obtained for the box 11 is the 32.2 kilopascal, and then the air entry value for the box 2 is 658 kilopascal. And here is the relationship between the instantaneous volumetric water content, which is used for the calculation of the water storage function. And then here is the water ratio versus soil suction. It presents a huge volume change during this drying process. And here is the saturated coefficient of permeability versus the soil suction. The relative coefficient of permeability is obtained from the degree of saturation, and here is a percent of the result. And also the coefficient of permeability is a product of the relative coefficient of permeability and the saturated coefficient of permeability. So my conclusion is conventional estimation techniques based on the assumption of no volume change are not suitable for soils that undergo volume change as soil suction is increased. A revised methodology for the estimation of the coefficient of permeability function and the water storage function for high volume change materials is presented. Both the water ratio change and the degree of saturation are considered as the influencing factors. Experimental data of grammage water content, SWCC, and the shrink curve and saturated permeability are required to appropriately estimate the coefficient of permeability function and the water storage function for high volume change materials. So in my last minutes, I want to give my thanks to COSIA and ANSWER for their financial support, and also my thanks to my supervisors, Dr. Wilson and Dr. Ferrand, for their guidance and their advice in my program and in my life. And also I want to give my special thanks to Soil Vision for their financial and technical support. Thank you.